Hey, what's up, guys? Welcome to my Algebraic geometry video. And so this video, I want to talk more on Stalks and prove the two main results that usually people talk about Stalks, and so that we can talk about sheaf location. So basically, I want to make some detail at the previous two video about the morphism and the sheaf of morphisms. Sorry, the morphism of sheaves. Okay, so that's quickly let's go through the definition of Stalks and prove some basic results. Oh, hope you guys subscribe to my channel. Right, so let's say X is a topological space. Right, and so given a sheaf, right? So given a sheaf, that you can define a Stalks. So basically, Stalks on each X belongs to X is defined to be let's say US. Where X belongs to U, and the S belongs to the sheaf of sheaf tag value on this, right? So remember, sheaf is just basically for each open set, you need to give me like abelian groups or ring or any abelian category or module. And the modulo some relation. And this relation simple, just some people call germs. So basically, we're just saying that if U S equivalent to US prime, if you can find the open neighborhood or open subset U intersection with U prime, such that when you do a restriction, right, there's a restriction map on the sheaf. So you can restrict it U to W, the same as prime, U prime W. Okay, and you connect all of them, right? Then this is called the Stalks at X. Okay, so I think this is simple, right? Just write down a definition, and hopefully everything still looks good. Okay. So first theorem that is very simple that we should prove is that so given F, right? You can take U, right? So there's a natural map. There's a natural map from this to basically given U, right? There's a natural map that for each X belongs to U, can take the Stalks. So this is the product, right? So U may be uncountable, but it's fine that I can define the products between this F of X. So this is given FU, I define this. Okay, so this map is given U. Given U, you give me U, then I can give you this. I can map this F of U to take the sheaf Stalks F of X and takes the X belongs to the collected X. Okay. So this is there's a canonical map. Okay, the important theorem is that this map is injective. This map is injective. Okay, so this is that we need to prove. Okay, so what? So I'll just write down definition. So let's say we have S prime, and then we hope to prove that if they are the same, then we hope to prove that if they map to the same thing, then they are the same. Okay, so proof is very simple. Right? So let's write down definition. So if I map to here, that means that for X, right, that each component is the same. So I have U S equivalent to the U S prime. In this case, that X belongs to S is subset is an element of U, right? For each X, I have U S because this is the form of in the element in the Stalks. Okay? So you have US the same as US prime for all X, such that X belongs to. So basically, you take every X, and they are the same thing. Okay, so basically you have Bx which depend on X, right? In a subset of usually it's U intersection with U, right? But it's fine that U intersection with U is U. Okay, so such that S restricted from U to Bx is the same as S prime restricted U to Bx. Okay, but we know that the U, right, is intersection with it's a union of each x. Okay? So this means that this globe, this section are agree on all the open on each cover. Right? So this is open cover. So on each open set. Okay, so by the definition of the sheaf property, of F, then we get the S is the same. Okay, right? Because the property of sheaf says that if you have two guides which agree on each subcover for each open set, then it should be agreed on the whole space. Okay, so this is the first theorem. I think so. We will use this theorem is important because in the future that if we talk about sheafification, then you will need this theorem. So basically, these guys is important. Okay. Okay, and theorem 2 that is very supposed that so this given any x, right? If you have a set ax, so ax can be arbitrary guide, right? And the theorem tells you that x belongs to U. So if you define this is called F, or basically some guide for L. So this is ax is any set. Okay. So this proof is very simple. Because this doesn't have any structure, right? So we just say x set. So you should imagine that this proof just start from x. The proof is very simple because if you only consider the only thing you need to prove is that if they agree on intersection, there must be a guide which come from AU. So basically, what I'm saying is that if you have some UI section of J, such that by the way, so we need to define a restriction map. Okay? So what's the natural restriction? So natural restriction will be just if B is a subset of U, then I can just make the product of AX. I just neglect the product, neglect the element which is not in B. So this is a projection. Just projection every coordinate which is not in B, throw it away. Okay. So this is the restriction map. Okay. So in order to prove this one simple, right? So you just imagine that you imagine that let's write it carefully. So let's you imagine that if you have Si Y and Sj on J, you want to say that they are the same in the right. So if they are the same on UI Uj, for simple, you're just saying that Xix, right? Because for each x belongs to the UI intersection J, because now just projection, right? So here's Sjx Y intersection J, and you want to prove that there is a guide which you want to prove that it is S when S restricting on Y from U should be Si, and then S restricting from U to Uj should be Sj. But this is trivial, right? You just take S to be the when S on the okay, so you just take basically you just take the S to be such that when X belongs to Y, then you just take to be still Si. Okay. And if you take X belongs to Uj, then you just take to be Sj. Because they are already coincident on the subset, on their intersection. So this stupid map is trivial, right? It's trivial satisfied. Because if X belongs to UI, you define by Si, then by definition, by this projection, it's just this. It's just this. Okay. So this S just take to be like just define to be this. Yeah. Okay. So this tell you that these guys are sheaf. So theorem 3 is that I think it's the sheaf morphism that morphism sheaf that I have not yet proved. But the proof is simple that this theorem just tell you that you have G. These are morphism sheaf. And you define this thing to be the so definition is that usually when I say phi is isomorphism, if they are the same on each stocks, so basically we're saying that so phi x will introduce maybe let's not say this. Let's prove it out. So this theorem should be do as this. If I have phi from F to G and another map, another morphism called psi from F to G, and then there are morphism sheaf. So I will say that if phi equals to psi on each x, then the phi equals phi of u, then it's psi of u for any open set. Okay, so this is the theorem that you will commonly use in algebra. So when okay, so this proof is that one direction is trivial, right? But in this direction, because your stocks can be viewed as you can use co-limit, right? You can use file. You can use the stocks as co-limit. You can define the stocks written in co-limit. So if there are agree on all the open set, then sure it should agree on. It should be the same as stocks. So this is why it's by definition of stocks. And so the non-trivial proof probably is this one. So this is why we need the previous results, right? Because so basically we want to say that these two are the same, right? So we can take F, G, and oh, maybe let's take F and G, and we just proved that there's a map which is powerful. Let's say when U, this map is X belongs to U F X, and product of X belongs to U G X, right? And so there's a true map which is phi and psi, and then these are two map. Okay. So if there's a sheaf of morphism, right, then it will introduce some maps between the stocks, right? So this will induce a map called X from Fx to Gx. So phi and psi x x of f of x. So these are for all x. This okay. So maybe I shouldn't write like this. Maybe I should write it's fine. Okay. So this one is there's a map called phi of x. Here's a map psi of x. Right? So phi of x map f of x to g of x. Psi of x also map f of x to g of x. Okay. And this means that they are the same for x. So they are the same map. This is the same as right? Psi of in the right hand side, it's the same as same for them. Okay, so okay, so now we know that this map has been proved. These two are injective. Okay, so that means if they are the same, this means that since they are injective and these are exactly the same as a map, so that means that this map need to be the same, right? Because these two are injective and these two maps are. So if you map the same every point as a set, right? Map this guy as a set. Exactly set. That they agree on they agree on each. They agree there are this map they are the same, right? So and these two are injective. So as a set, these map fixed and then these are injective. So that means that these two must be the same to make these direct count, right? So 5u sub u for okay, and we're asking that for every x, right? So which means that this is true for every open set. If there, so it's like if you have two morphisms, they agree their maps in there induces set maps on stocks. They induce set maps on every stock their points. Then they will have the set map on every open set. Just by injectivity between these two maps. Okay. And I think this is these are basic property of stocks that people will keep. Okay, so see you guys next.